Good morning. I'm gonna try an easy question here since I only have 30 minutes. So, okay, let's have a look. Okay, timer. Let's go. Symmetric tree. Symmetric around center. Okay, so it's a mirror. Um, mm, so if we had more children under here, say we have 5 and 6, that would be 6 and 5. That would be symmetric. Okay. Mm. Hmm. So I'm thinking, we have the root node, and then left and right of the root node, they gotta be the same. And then from that point downwards, we basically need to check all the left nodes to compare that with all the right nodes and see if they are the same. For each node under that. Okay, let's see if we can write it recursively. If root is null, we return true. This we might be able to optimize later, but for now, if that's not the same, that's not symmetric. Okay, then we want to go recursively into all the children of these and these. So we would be comparing, let's say we are comparing root left with root right. they're not the same, return false. Otherwise, we wanna go if left is not null, or if it is null. So that should take care of all the cases if any of them is null. Okay, so now we have if they are not null, then we can do value not the same, return false. Otherwise, we go to the children node if when we're gonna compare left with right. So we're comparing that with that, and we also need to compare these. Right and right left. Then we need to return okay, it's only true if both of them are true. Otherwise it's false. Okay. Let's see if this works. Okay, so that worked. Let's just refactor a little bit. Alright, so that's the recursive solution. Let's think. Time complexity. Alright, time complexity. We will need to go through all the nodes and what is happening when we are doing compare. So we do compare those, and we compare those, compare those. And when we're in here, we need to go one level down. I'm thinking that it's linear time, but I'm not very sure because recursive sometimes lead to a much worse time complexity. But in this case, it seems to be linear, O of n, to the number of nodes in the tree. That's what I'm thinking right now. And space would be constant because we're not using another structure to store anything other than the stack when we're going to this recursive routine. Okay, how would we do it iteratively? Might have to use queue or stack. Okay, so if we use a queue or stack, and then instead of pushing or queuing in the normal order, we do flipping left and right, would that work? We actually really need a good example that's bigger to see if it works well. Usually if we have like a really good example covering a lot of cases, that would be the most helpful. Alright, let's just imagine we have 5 and 6 here. 5 and 6, so that's null. We have 5 and 6, so this should be 6 and 5 in order for it to be symmetric. And what will happen if we do a queue? So we have this to be the first in the queue, and accordingly this to be the first in the other queue, and then we queue the left one, we in queue left, in queue right. Okay, then we need to handle the children. Okay, what if we in queue these also right away? Okay, so we in queued 2, 3, 4, 2, 3, 4, and then we can dequeue that. We dequeue that because we are already done handling their children, and then we have these in front of the queue. Now we dequeue those to see if they have children. If they do, we will enqueue the left one and enqueue the right one, and then enqueue the right one, enqueue the left one. And now that is dequeued, the next one in the queue is 4, and we will do the same thing, compare their values, and then enqueue their children in the opposite order for the left and right halves. So that should be a working algorithm. Let's see if we can write that. So we have a queue of 3 nodes. So we do need 2 queues because we need to compare the right with the left halves. Okay. Queue left. Well, let's have this for now. Well, we still have the case when one of them is a null node, so we cannot do just dot val. If left is null or right is null, okay, I guess let's do this. If left is null and right is null, then we actually don't need to do anything. We just go to the next round, I guess. Okay. Else, if left is null or right is null, so they're now both null but one of them is null, then we can just return false for the whole function because they're not symmetric. Otherwise none of left or right is null. We will compare their value. Okay, so if they are the same, if this node is symmetric, we wanna Q left in Q left left, Q left in Q left right, and Q right in Q left right, and Q right in Q right left. So left left, right right, and left right, and right left. Okay. So that's the idea. Let's see if this works. Otherwise, we will make adjustments. So if we just take this for example, oh, great, that worked right away. Okay, let's see if there's anything we could do to refactor it. So for this iterative algorithm, the time complexity would be linear because we're just going through the tree one node at a time, and then enqueuing the children nodes and dequeuing the nodes we already looked at. So that would be linear time, but it will also be linear space because we are using two data structures to store those nodes. Although we are constantly enqueuing and dequeuing, so we actually never stored more than whatever that's on the last row. So we enqueue these and we dequeue them right away to enqueue these, and then we go through these one by one to enqueue their children, but we also dequeue them right away. So the space would not exactly be the whole binary tree. It would rather just be at most the row that had the most children. That's where it will be the most. So I don't think that will be counted as constant because we don't really know the row that had the most children. So I guess it will have to be linear, but it's definitely way less than the entire tree. Okay, let's take a look quickly to see if we can refactor. I do have to leave in 5 minutes. So that's not really defactoring anything, just okay, if they're both null, we will continue. So in the case when that is null and that is null, well, we could adjust it to be if the node is null, we will not enqueue it. I guess that would be a little improvement. So here, instead of enqueuing the left right children, we will only enqueue it when it's not null. Then we don't have to check the case when both of them are null, because that would be kind of just wasting more steps. Let's see. We will need to add all of these. Left is now null. So we no longer have this case. We will still have, okay, we do not have left is null or right is null either. Just if left value is not the same as right value. Okay, let's see. Very interesting that how interesting. See, that actually misses the case when it's because the order of the left or right matters, because now we will be not enqueuing anything there, so that would just be the next one in the queue, and the queue cannot see if that is the left or the right children. Interesting. Alright, so that did not work. It's good to know. Let's go back to the original one. So yeah, the point is that we do need to enqueue those null nodes in order to be able to mark the order of the tree. So we have null 3, and we're comparing that with 3 null. If we do not enqueue those null nodes, it would just be 3 after 2 in the queue, 3 after 2, and they would just be considered to be symmetric even when they're not. Alright, I think I'm done with this exercise. I don't have time to look through all the solutions right now. Let me just check quickly. Recursive. If one of them is null, we just return that. So that is a little smarter way to handle the case when one of them is null. Okay, so also return that and that instead of writing out and assign 2 extra variables like I did. So the idea is the same, more compact code. Let's see. Okay, so they're using stack. Okay, so they are only using one stack, and that's why the algorithm is different. Look at this. If you have one stack, push left and right. When it's not empty, we pop both of them. Both now. Oh, that's exactly the same as. Okay, left and right, right and left. So that's the order they're pushing. They're doing left, left, right, right. Okay, so they're doing the exact same thing, but they're doing it in the same stack, and then they pop out 2 at a time to compare instead of 1 in each stack. So yeah, it doesn't actually save more space because we are still pushing and popping the same amount, just here in one stack instead of 2 that I have. Okay, left, right. Okay, there's a queue. Adding a left and right. Okay, exact same idea using a queue. Alright, then I am pretty happy with this one. That will be it for Symmetric Tree. We'll do another one later. Oh, okay. Alright, well, that's it for this one.